Hello, this is Dr. Kraus with EGR 345, video 17, shifting into Root Locus. Root Locus is a control design technique. Many of you have kind of already been asking, okay, I've got a transfer function. What good does that do me, or how does that help me design a control system? And so we specifically want to talk about, so if G of S is our plant and D of S is our controller, how do we choose D? Up until now, all we've done is PID tuning and kind of guessing whether or not we need I or D or whatever. So we want to shift gears from this kind of guess and check tuning approach, which can be effective and was all that we knew up until now, to something that is more like a real design process with constraints and specifications and whatnot, but also something that is analysis and simulation driven. And so we're not just guess and check, guess and check, guess and check. So when I say PID tuning, I mean just kind of tweaking KP, tweaking KD, tweaking KI until you get something you like. If that leads to an okay controller, that's not bad. It's quick, it's easy. But it doesn't apply to all systems. There are some transfer functions where it simply isn't going to work, and then or where PID isn't the right form. And then there's other situations where, okay, you got it working, but how do you know if you could really do better or if that's the best you can do? And so understanding how to do control design will help you answer those questions. And there's I don't know, 2, 3, 4 primary ways that people do control design, and Root Locus is probably the most common one that people start with. So, what is Root Locus? The Root Locus is a graphical control design approach for tracking how the pole locations for a closed loop system move as a parameter is varied. Locus is a mathematical term talking about showing a collection of things. So these are branches that show a collection of all of the closed loop poles. So what we're doing is tracking the closed loop poles, and that's key. These are the poles of the closed loop system based on the open loop transfer function, which is also key. We never have to find the closed loop transfer function explicitly. We're doing this based on the open loop transfer function. And in order to do this, we are going to need to factor out whatever one parameter we want to vary. So how does this work? What's the mathematical foundation from it? So we've got this typical unity feedback transfer function, block diagram, closed loop system. And we know that if we work this thing out, we've done this before, that the closed loop transfer function would be dg over 1 plus dg. So we know that the poles of this closed loop transfer function are when the denominator is equal to 0. So this equation, also called the characteristic equation, tells me the poles of the closed loop transfer function. So if I could solve this, I could find the closed loop poles without having to go through all of the hassle of finding the CLTF and kind of simplifying it or whatever. Especially if there's parameters in here that I want to leave as symbols so that I can vary them, which we kind of did that in one of our previous labs. Now, this, because I said we got to factor out whatever the one parameter, usually called k, that we want to vary. This is not our standard form. We want to convert this standard block diagram to kind of a standard root locus block diagram. So L now is sometimes called a loop transfer function or a forward transfer function or whatever. But k times L, this has to be the same block diagram as the one up here. So it has to be true for this to be valid that d times g is the same as k times L. So we're factoring out a k from here. Usually that's done by factoring the k out of the controller transfer function and leaving g alone. So if we define d hat to be d with the k divided out, then L would be d hat g, and then d hat g times k would just give us back dg. So this is kind of standard root locus form. And then the fundamental equation, if we have this form, then our CLTF or our G sub CL is just KL over 1 plus KL. So the characteristic equation becomes 1 plus KL. And it seems ridiculously overly simple, but that is the foundation of the root locus method. Now we do one other, or maybe two other, very trivial seeming steps that get us into the magnitude condition and the phase condition, which are the foundation of root locus. So we take 1 plus KL, and we subtract this 1 over to the other side. I know that's really, really fancy math. But we end up with KL has to equal negative 1 for all of the poles of the closed loop transfer function. Even fancier math, we take negative 1 and we seemingly, for no good reason, separate it into a magnitude of 1 with a phase of minus 180 degrees. So KL has magnitude 1 and phase of negative 180. Repeated here for convenience. Since K is a positive integer, it's not going to contribute any phase to the system. So the phase condition, which we talk about all the time in controls textbooks when we get to root locus, is simply that for all points on the locus, the phase of L has to equal negative 180 degrees. So the root locus graphically represents all of the points on the real imaginary plane where this phase condition is satisfied. And so this right here is the foundation of probably 3/4 of your root locus sketching rules, is that we have to satisfy this phase condition. So again, I know it seems simple. It's coming out of here, which is leading to this, which is leading to this, which is leading to this. It is not rocket science on the surface of it, but this turns out to be super powerful for a graphical approach to finding the angles contributed by every pole in 0 so that they add to negative 180 for the points that are on the root locus. Then, so it's typically done, we draw the root locus for K going from 0 to infinity, and then if there's a specific spot where we would like to place our closed loop poles, then we need to find the K that goes along with that spot. Well, if we know so if KL is magnitude 1, phase of negative 180, then the magnitude of KL is 1. Again, K is a positive real number, so we pull that out, divide the magnitude of L across. Again, super complicated math. K is the magnitude of L. So at any point on the root locus, we evaluate the magnitude of our loop transfer function. 1 over that tells me the K that would cause the system to go to that closed loop pole location. So with that, let's do a quick example of taking this transfer function and putting it under proportional control. So KP will be the K and G will be the L that we were talking about. Let's quickly sketch the root locus of this and talk about the implications of it. So here we are with a relatively simple plant. We're going to put this under P control. Now you could take KP times G over 1 plus KP and solve that and get a symbolic form. And you actually did this in one of your labs. And you could see how KP affects the closed loop transfer function. Not terrible because this is a relatively simple system with a relatively simple controller. I'm going to argue that once you learn how to do root locus, this is trivial and can be done in less than 30 seconds. So first of all, I need to know my poles and my zeros. Just like we would with a Bode plot, we need to find those first. Root locus, completely different in some ways, but still need the poles and the zeros. So the roots of this based on the quadratic formula. So I'm looking for the roots of s squared plus 2s plus 10 equal to 0. Those are my poles. By definition, the roots of my denominator equal to 0. So the roots by the quadratic formula will be a negative b plus or minus the square root of b squared minus 4ac all over 2a. So this is in negative 36 square root over 2. The square root of a negative 36 is 6j. So we've got a negative 2 plus or minus 6j over 2. Or s is equal to a negative 1 plus or minus 3j. So that'll turn out to be almost by far the most time-consuming part of this example for me. So if I then sketch my poles, and there are no zeros, on a real imaginary axis, I would come over here to, so this is -1 plus 3j and minus 3j, like so. And then based on my knowledge of the root locus, I know that the points that satisfy the phase condition will go like that and like that. So as I crank up KP, I'm going to go straight vertical up and down with my poles. What that means is because this real part is negative zeta omega n, and this part is j omega d, and this radius is omega n. We've kind of talked about those things. We could review that if we needed to. My zeta omega n product would remain constant because we're going straight vertical. So omega n is going to go up as I crank up k, but if omega n goes up and this product remains constant, then zeta has to come down. And so I can see right now by looking at this that my settling time never changes, and we'll talk about settling time and define it mathematically soon. My settling time is never going to change. My natural frequency is going to increase. Damping is going to go down as k. So as k goes up, omega n goes up, and zeta comes down, and zeta times omega n remains constant. And you came to those conclusions doing this symbolic stuff, but it took a little bit of time. I'm saying if you knew the poles and you knew that there's two of them and that they are complex, boom, root locus done. So that's where we're headed. I want you to learn how to do this kind of thing quickly and easily. Yes, of course, a computer, Python, MATLAB, whatever, can do this for you. Just like with the Bode plot, I want you to know how to draw them by hand quickly with reasonable accuracy for a number of reasons that we will talk about soon. So one last thing to talk about in this introductory video. Certainly there are many root locus videos on YouTube. I would say when it comes to teaching root locus, there are two primary approaches. Approach one says, hey, all you got to do is memorize these steps. And maybe there's 4 steps, and maybe there's 6 steps, maybe there's 10 steps, depends on who you ask. But just memorize some steps, crank them out. You don't need to know where they come from, just memorize them, and boom, root locus, done. Or option 2 is to understand a couple of key principles, and if you truly understand those principles, then you can quickly rederive all of the steps knowing exactly where they came from because of your knowledge of principles like the phase condition. So if you're one of my students, man, you're just sitting on the edge of your seat wondering which of these two approaches I'm going to embrace, and you'll find out in the next video.